Okay, so let's have a look at a past paper. We're looking at Physics Higher Paper 1 from the Trilogy version of the Combined Science. Now, the link is underneath. I highly recommend you download that link, have a go at the past paper first before going through the answers explained with myself. Now, looking at this first question, we have two diagrams of the atom. We have the older plum pudding model and the more newer nuclear model. We have some words to choose from, and we've got to fill in the missing blanks. So on the plum pudding model, the negative particles were the electrons. The diagram is of the atom, and then when we move across to the nuclear model, we can see that the middle of our atom is called the nucleus, and the electrons lie on our orbits. Now, if we look at our second question, we're being asked to explain why the total positive charge in every atom of an element is always the same. So the first thing that we need to do is we need to state that every atom on the periodic table, which is of the same element, will have the same number of protons. So if I have an atom of lithium, it will always have 3 protons. If I have an atom of carbon, it will always have 6 protons. Now, if it has the same number of protons, then the protons are positive, so every atom of an element is going to have the same positive charge. So now moving on to the next part, it says the results from the alpha particle scattering experiment led to the nuclear model. Alpha particles were fired at a film of gold at a speed of 7% of the speed of light. Determine the speed of the alpha particles. Now the speed of light is 300 million meters per second, so we need to find 7% of that. So the way that we would do that, we would have our speed of light, and we would multiply that by 7%, which is 7 out of 100. And if we calculated that out, we should get an answer of 21 million meters per second. Now we could write that in standard form, so we could put 2.1 times 10 to the power of 7. Either way would be correct. Now moving on to our next question, we have two atoms, one of hydrogen, one of magnesium. We're told that the hydrogen atom has a radius of 2.5 times 10 to the minus 11 meters. Determine the radius of the magnesium atom. So we need to get our rulers out and we need to measure how large our hydrogen is compared to our magnesium. Now, if I measure my hydrogen, I get 1.3 centimeters, and if I measure my magnesium, I get that to be around about 7.6 centimeters. So I have to work out a ratio of how much bigger is the magnesium compared to the hydrogen, and I would do that by dividing my 7.6 by my 1.3, and that tells me that according to my measurements, magnesium is 5.8 times bigger. So I can do a calculation now to determine the radius of the magnesium, because I can do the radius of the hydrogen atom, which was 2.5 times 10 to the minus 11, and I times it by how much bigger my magnesium is, which according to my calculations was 5.8, and then I would get an answer of 1.5 times 10 to the minus 10 meters. Now, in your answer, you are allowed a range, so the range would actually be from 1.4 to 1.6 times 10 to the minus 10. Now, sometimes when you have 6-mark questions based on practicals, it is good to use diagrams to help with your explanation. So the first thing I would do is I would say how I'm going to work out the density. So the formula for working out density is mass divided by volume. So the first step is I would use a balance to measure the mass of the object. Then, to work out the density, I need to work out the volume. So to work out the volume, what I would need to do is I would need to lower my object into a Eureka can so that we can collect the water displaced and measure the volume of the water displaced. Okay, so it's not necessarily it's not necessary that you have to do a diagram, but sometimes it helps just to make sure that your explanation of the method is clear. And then for your final point, you need to say what you would do. So you're going to calculate the density by dividing the mass by the volume collected. And there you have it, a nice clear method. Now for this next question, we have a student that's done a similar experiment. He determined the density of some common plastic materials. So we've got acrylic, nylon, polyester, polystyrene and PVC, and we have their densities. So the first thing that we have to do is we have to determine the scale that's been used on the graph that he's plotted. Now, if we look at the acrylic and the nylon, the correct scale would be for each of the large squares going up in 500s. So you just write that on your y-axis to get some marks there. Then we have to draw the bars for the missing plastic materials. So if we draw the graphs in, you can see that you have to be very accurate. And the key thing is that you realise that on our scale, 2 small squares represent 100. So if we draw in our bars for polyester, polystyrene and PVC, for polyester we have 1380. So it's important that you don't take it up to that next square, it's just under. For polystyrene, it's 1040. So again, you go up to 1000. One small square is 50, so it needs to be just under. And then for PVC, it's 1100. And for this one, the examiners are just trying to make sure that you've understood that 2 small squares is 100, so it should be on that straight line. Now, you don't need to waste your time colouring these blocks in. You just need to make sure they're in the right place. And for drawing the 3 of those, you would get 2 marks. And for getting 3 of your axes labelled correctly would give you 2 marks as well. For this next question, the student is given a piece of different plastic material. So the students worked out the density 3 times and we've got their results. And we've got to determine the uncertainty of the student's results. So first of all, uncertainty is a half times the range. Now to work out the range, it's the largest result, take away the smallest result. Now we've got to be careful here because the largest result is the second one. So that would be 1120, take away 960. So our range works out at 160. Then we can do our calculation. So it's 0.5 times what our range was, which was 160, and we get an answer of 80 kilograms per meters cubed. Now, if we look at question 3, we have a diver who has a canister of compressed air, so he's able to breathe underwater. And the question is, which 2 sentences describe the movement of the air particles in the canister? So we've got to tick 2 correct boxes, not 1. So the first one is they vibrate about a fixed position. Well, that's not true, that's for a solid. They move in random directions. Yes, gases do that. The motion of the particles is predictable. Well, no, for gases it's very random in all directions. They move with a range of different speeds, so that sounds like it would be correct. And they move in circular paths. Well, that's not something that we could predict. The next question says that the temperature of the air inside the canister increases. What happens to the movement of the air particles? So for the temperature of the air in the canister to increase, the particles have to gain kinetic energy so they can move around faster. For this next question, it says it could be dangerous if the temperature of the air inside the canister increased by a large amount. Explain why. Now, when we're answering this question, it is important for us to remember that as the temperature increases, the pressure also increases. Now, if the pressure inside the canister has increased, that means that could lead to an explosion. Okay, so now for the next part of the question, it says a canister of air was tested to find out how the pressure changed when it was used by the diver. Air was allowed to escape from the canister. The pressure of the air in the canister was recorded every 5 minutes for 80 minutes. So estimate the atmospheric pressure. Now, for us to estimate the atmospheric pressure, that's going to be achieved when the pressure inside the canister is going to be equal to the pressure outside. So that's going to be shown on our graph from when the pressure starts to level out. So what we would do is we would get our ruler and we would draw a line from where we're starting to level out to the y-axis. And if we go to the y-axis, we can see that it's one small square up where it's leveling out. And if we have 0.5 being 5 small squares, then one small square is going to be 0.1 megapascals. Now for this next part of the question, it says the drivers can safely stay underwater until the pressure of the air in the canisters has reduced by 25% of its original value. Determine the maximum time the driver can safely stay underwater. Now it's key to remember that depending on the question, it can be a follow-up question from the first part. So we do have to go back to look at the graph to work this out. So first of all, to work out what 25% of the original value is, we've got to work out what the original value is. If we look here, we started off halfway between 2.0 and 2.5. So halfway between those two numbers would be 2.25 megapascals as our starting volume of gas. So to get 25% of that, 25% is 0.25 times the starting value, and that gives us 0.56 megapascals. And 0.56 megapascals now on our y-axis would be roughly halfway in between here and here, because each small square represents 0.1. So if we go across and we go to halfway between those two squares and then we draw a line downwards, we would get our value at being we would get 26 minutes. So from our calculations from the graph, we had 2.25 times 0.25, which gave us 5.6, and when we worked that out, we got a value of 26 minutes. Now, there is a range that the examiners will accept here, and the range that they're accepting is from 26 to 28 minutes. Now, the next question says, what happens to the volume of the air when it's released from the canister? And if the volume of the air is released from the canister, then then the volume of the air. So the next question says, what happens to the volume of the air when it's released from the canister? Now, because the air is compressed in the canister, when it's released from the canister, the volume of the air would increase. Now, for this next question, it says the Chernobyl disaster was a nuclear accident and happened in 1986. Radioactive isotopes were released into the atmosphere. The radioactive isotopes emitted alpha, beta, and gamma radiation. So what is an alpha particle? So an alpha particle is an helium nucleus, which therefore would have two charged particles and two neutral particles. Then the second part of the question is asking about beta radiation. Which of these comments is true? So beta radiation is fast-moving electrons, so they would be the type of radiation with a negative charge because they are an electron. The next part of the question is asking us about gamma radiation. So it says gamma radiation, it has a low frequency electromagnetic wave. Well, that's wrong because it's not low frequency. It causes the change of the it causes the charge of the nucleus to change. That's not true because it's not a particle. It causes the mass of the nucleus to change. Again, it's not a particle. And it has a very long range in air. That one is actually true. Now, if we look at this next question, it says Table 3 shows the half-life of two of the radioactive isotopes that contaminated the environment. So we have our results there for cesium-137 and iodine-131. A soil sample was taken from the area around Chernobyl in 1986. The soil sample was contaminated with equal amounts of cesium-137 and iodine-131. Explain how the risk linked to each isotope has changed between 1986 and 2018. Both isotopes emit the same type of radiation. So we can see that with cesium-137, that's still going to be high risk because the half-life is still very long. Whereas with iodine-131, the risk is going to be quite low now because the half-life is very short at 8 days. Now, when we look at this next question, it says determine the year when the activity of the cesium-137 in the soil sample would be 1 over 32. So we've got to work out how many half-lives that would be. So if I do a half times a half, that's 1 over 4 times a half. That would be 1 over 8 times a half, 1 over 16 times a half. That would be 132. 1 over 32. So we have 1, 2, 3, 4, 5 half-lives. And if we then use that to do our calculation of 30 years being the half-life, we would have 5 times 30 because we've got the half-life from our table there. And that would work out at 150. So then we would do our year, which would be 1986 plus the 150 years, and that would give us the year 2136. Now, when we look at this next question, we have a wall that has cavity insulation with layers of brick insulation, then we have our blocks on the outside. So it says, explain how the wall reduces unwanted energy transfer. So first of all, we need to make the point that the wall has multiple layers. And given an example of that, we can say that this type of wall is a cavity wall, which means it has low thermal conductivity. And therefore, if it has low thermal conductivity, this means that the wall is actually going to reduce the heat transfer by conduction. Now, we have some results in this next question. We've got the cavity insulation being tested. So the heating inside the house is switched off and the temperature is measured every 20 minutes for 2 hours. And then we've got our results table here. We've got to determine the temperature inside the house after 30 minutes. Now, 30 minutes is in between these two timings here that we have results for. So we have a range of temperature going from 20.8 to 17.4. So we need to find out what halfway in between those temperatures would be. So the way in which we would do that, we could have 20.8 take away 17.4 to tell us what the difference between those two are. And then if we divide by 2, that would give us halfway in between. Now, we can either add whatever our answer is to 17.4, or we could take whatever our answer works out to be away from 17.8. And that's because as the temperature is increasing, as the time is increasing, the temperature is decreasing. So what I'm going to do is I'm going to work out what halfway in between those two were, and I am going to add it to my 17.4, and that would give me an answer of 19.1 degrees Celsius. Now, if we consider this next question, we have a gas boiler where the fuel is being used to heat up cold water, which then turns into hot water, which then heats up the hot gases in the atmosphere. So the question is, describe how the different energy stores are changed by the boiler. So first of all, the chemical energy store of the fuel is going to go down as the fuel's being used up, and that's going to be transferred to the thermal energy store of the water, which will increase. And once that happens, then that thermal energy store is going to heat up the gas particles in the atmosphere around it. So the chemical energy store, so the thermal energy store of the air would therefore increase. Now for the next question, it says to heat the house, the boiler transfers 15 megajoules of energy in 10 minutes. Calculate the power of the boiler. So the equation that we're going to have to use here is power. So the next part of the question says to heat the house, the boiler transfers 15 megajoules of energy in 10 minutes. Calculate the power of the boiler. So the power of the boiler is going to be the energy transferred divided by the time taken. And the energy transfer has to be in joules. So we would change that into joules divided by the time taken, which needs to be in seconds. So instead of 10 minutes, we need to change that into seconds, which would be 600 seconds. And if we calculate the power, we would get 25,000 watts. So that is our answer, 25,000 watts. In this question, a student built a circuit using a filament lamp. Sketch a current potential difference graph for a filament lamp. So it should look something like this. Now in this question, we've got figure 10, which shows the circuit with two identical filament lamps. So basically we have a parallel circuit. We've got to compare the current I1, I2 and I3. So for this type of circuit, the current going into the circuit is equal to the current in the different parts of the parallel circuit. So what we would say is I1 equals I2 plus I3. Okay, for this question, we've got to calculate the charge that flows through a cell in 1 minute. So Q, the charge, is what we are trying to work out. We have a time, which is 60 seconds, 1 minute. Each filament lamp, so we've got 2 filament lamps, each of them have a power of 3 watts and a resistance of 12 ohms. And we've got to work out the charge. So first of all, we know that we have an equation where charge is current times time. However, we do not know the current, but we could use power is current squared times resistance to work out the current. So if we use this equation first, so if P equals I squared times R, which is current squared times resistance, we could rearrange, so current squared is power divided by resistance. And then current would be the square root of power divided by resistance. And if we put our numbers in, current is going to be our power, which is 3, divided by our resistance, which is 12, and our current will work out to be 0.5 amps. Now, we can use our current now for our second equation because charge is current times time. So our charge is going to be our total current. Now remember, we've got 2 lamps, 2 filament lamps. So that's going to be 0.5 times 2 because we've got both lamps. And then we're going to times that by our time taken, which was 60 seconds. So our charge is going to end up being 1 times 60, and that means our charge therefore is 60, and the units for charge is coulombs. If you get the answer wrong, but you've got the units right, you still get 1 mark for this. Now, if you did not times the charge by 2, you would only lose 1 mark out of the 6. So the things that you would get your marks for is, first of all, working out our current and using the right equation there. You would get a mark for the rearranging, and we would also get a mark for actually saying that the current is 0.5 amps. You would then get a mark for your second equation where charge is current times time, and you would get a mark for the doubling of the charge. So that's 1, 2, 3, 4, 5, which would then mean you got your correct answer and you get your mark for the correct unit. Okay, so in this last question, the student builds a different circuit, and we have a diagram here, and we've got to explain how the readings on both meters change with environmental conditions. So first of all, because this is a light-dependent resistor in our circuit, that means that as the light intensity increases, the resistance of the LDR is going to decrease. Now, if the resistance of the LDR has decreased, that means that there's going to be more current going through our ammeter. But also what that means is, in terms of the potential difference, because we have a fixed resistor here, our fixed resistor is going to get a higher proportion of the potential difference, which means the LDR would get a lower proportion of the potential difference. And that in turn would mean that if we have a lower potential difference here, the reading on the voltmeter would decrease. So that's the end of the walkthrough on the Paper 1 Physics for AQA, May 2018. I really hope you found this useful. If you did, please do hit that subscribe button, and you will have access to more past paper questions on all aspects of science. So that includes biology and chemistry too, as well as lessons learning on topics as well.